Chapter 3, Segment 4. The site of selective adaptation effects. The adaptation experiments replicated here provide strong evidence that the orientation and spatial frequency are coded by neurons somewhere in the human visual system. Now, recall that information from the two eyes is kept completely separate in the retinas and in the two lateral geniculate nuclei. No single neuron receives input from both eyes until the striate cortex. The transfer of adaptation effects from one eye to the other thus implies that selective adaptation occurs in the cortical neurons. Spatial frequency tunes pattern analysis in human vision. The human cerebrospinal fluid actually reflects the sensitivity of multiple individual pattern analyzers. Spatial frequency channels. A pattern analyzer implemented by an ensemble of cortical neurons, in which each set of neurons is tuned to a limited range of spatial frequencies. The most likely explanation is that we simply have neurons tuned to low spatial frequencies. The multiple spatial frequency model of vision implies that spatial frequencies that stimulate different pattern analyzers will be detected independently, even if the different frequencies are combined in the same image. Graham and Nachmius found that the contrast sensitivity for this compound pattern was almost the same as the contrast sensitivity for detecting the individual components of the pattern separately. If the two component sine waves had stimulated a common pattern analyzer, then their effects on the analyzer should have been added, so contrast sensitivity should have greatly improved. Why would the visual system use spatial frequency filters to analyze images? Different spatial frequencies emphasize different types of information. If we want to know about the fine details, for example, whether the people are frowning or smiling, we must rely on our high-frequency channels. It is widely agreed that at near thresholds contrast, pattern analyzers operating at different scales or analysis are independent. At high contrast, however, pattern analyzers do interact. The development of spatial vision. William Jones described the infant's world as a blooming, buzzing confusion. If infants are shown two senses, they invariably stare at the more complex scene. An alternative approach is to measure visually evoked electrical potentials, that is, electrical signals from the brain that are evoked by stimuli, by attaching electrodes to the scalp and measuring the changes in electrical activity that are elicited by the changing visual stimulus. With this, we can measure an entire contrast sensitivity function in as little as 10 seconds in a non-verbal infant. Development of the contrast sensitivity function. At low spatial frequencies, contrast sensitivity may reach nearly adult level as early as about 9 weeks of age, where sensitivity at high spatial frequencies continues to develop dramatically. After birth, foveal receptor density and cone outer segment length both increase, as cones become thinner and more elongated. There is a dramatic migration of ganglion cells and inner nuclear layers from the foveal region as the foveal pit develops during the first 4 months of life, and not until about 4 years of age is the fovea fully adult-like. From birth to beyond 4 years of age, cone density increases in the central region because of both the migration of receptors and decreases in their dimensions. The massive migration of retinal cells and the alterations in the size of the retina and eyeball may necessitate the plasticity of cortical connections early in life. The peripheral retina appears to develop much more rapidly than the fovea. The girl who almost couldn't see stripes. The critical period is a phase in life span during which abnormal early experience can alter normal neural development. Amblyopia is a development disorder characterized by reduced spatial vision in an otherwise healthy eye, even with proper correction for refractive error, known as the lazy eye. Strabismus, a misalignment of the two eyes such that a single object in space is imaged on the fovea of one eye and on a non-foveal area of the other eye. anisometropia, a condition in which the two eyes have different refractive errors. Example, one eye is farsighted and the other is not.